we present our work, Independent Component Alignment for Multitask Learning. Here, we introduce a gradient optimization method for training multitask neural networks. This process is challenging due to conflicts and dominance among task gradients. We newly address these issues by examining the stability of a gradient system as measured by its condition number. Using this criterion as a design principle, we present an aligned MTL method that eliminates instability in the training process by aligning the principal components of a gradient system. Our approach has theoretical guarantees of convergence to a minimum with predefined task trade-offs. Extensive experiments demonstrate that aligned MTL consistently outperforms previous methods on a diverse set of multitask benchmarks, including visual understanding and reinforcement learning. In multitask learning, each task is associated with a specific objective function depending on a set of shared parameters. The training procedure is formulated as a minimization problem of a loss averaged across tasks. Recent works highlight the challenges that arise when trying to solve this problem via gradient descent. Namely, these are conflicts and dominance among task-specific gradients. We use a two-task synthetic problem to illustrate these optimization issues. Conflicts are related to a negative cosine distance between gradient vectors, while dominance is caused by an imbalance of their magnitudes. Despite existing methods aiming at solving these optimization issues, many of them provably converge only to an arbitrary point on a Pareto front. The Pareto front consists of points in which there are no gradients improving all problems jointly. Such guarantees are insufficient for multitask learning, since some Pareto solutions provide imbalanced performance across tasks and therefore are suboptimal. We are the first to tackle the multitask challenges from the perspective of a gradient system stability. The stability of a linear system is measured by the condition number of its matrix. The relation between the condition number and multitask challenges is straightforward. The condition number is optimal if, and only if, the gradients are orthogonal and are of an equal magnitude. In its turn, that means that the system of gradients has no dominance or conflicts. We exploit this criterion to create aligned MTL, a novel gradient manipulation approach that eliminates instability in the training process. Given an initial gradient system, we find its linear approximation subject to stability constraint. Since a condition number defines the system up to scale, we can use a minimum non-zero singular value, which is the largest scale that guarantees convergence to the optimum of the original problem. Accordingly, stability constraint gets reduced to orthogonality constraint, leading to the Procrustes problem formulation. Given a singular value decomposition of the initial gradient system matrix, a solution of the Procrustes problem can be found as a dot product of U and V matrices. It corresponds to a matrix with principal components being aligned. This can also be formulated in terms of left and right balance transformation of the initial gradient system. While being equivalent, these transformations have different computational costs, as typically there are much fewer tasks than model parameters. Thus, we operate in the task space and align gradients by finding eigenvectors of the corresponding gram matrix. This process has a straightforward geometric interpretation. Here, single task gradients G1 and G2 are directed oppositely and have different magnitudes. Initially, singular values are not equal, which indicates instability of the system. Our algorithm can be interpreted as rescaling axes of a coordinate system set by principal components. By doing so, we set all the singular values to be equal the minimal non-zero singular value. In the new coordinate system, the gradients are orthogonal and of equal magnitude, indicating the stability of the system. Finally, the aligned gradients are summed up with predefined task weights, giving a cumulative gradient. Within the Pareto front, the model performance may vary significantly. One of the advantages of our method is that it provably converges to a Pareto stationary point with predefined task weights, thus providing more control over an optimization result. Here, we visualize the optimization trajectories of different methods in loss landscape and loss-related frame. Unlike many other approaches, Our method does not terminate once the Pareto front is reached and converges to the global minimum. Moreover, as can be observed, aligned MTL provides the explicit control over the target point. The experiments show that our approach produces the least noisy trajectory among recent competitors. Through experiments, we show that aligned MTL consistently improves the performance of several multitask architectures on a diverse set of multitask learning benchmarks, including semantic and instance segmentation, depth estimation, surface normal estimation, and reinforcement learning.